All right, welcome everyone to the fifth exercise session, actually, of the hot track. Today we'll be looking at homotopes and retractions, sections, equivalences. And well, let's get it started. In the first exercise, we have a function f from a to b. And if you can't read anything, please let me know in the chat. A function f from a to b, and we also assume that we have a retraction g together with the homotopy. So we have g and homotopy, let's call it r, of the type retractions of f, and that is by definition the sigma type of functions g from b to a, which are left inverse to f. So g composed with f is homotopic to the identity on a. And we want to construct such a function from the retractions of f, well, to the injectivity proofs of f. And so yeah, at first we assume such a retraction, and we also we further assume a and a prime in a, and we also assume the proof p such that f of a is equal to f of a prime in b. And now notice that here, yeah, if we want to prove a is equal to a prime in a, we cannot use path induction here because our path is well, not in a, but our endpoints are. We're applying a function to it. But of course we have our function g, and we can apply this function g to this identity, and then we get g f a is equal to g f a prime, and yeah, so this is app g to p. Yeah, and then by our homotopy r, we can simplify this, because remember, this is really just a statement that for all a in a, g of f of a is equal to a. Yeah, so by our retraction applied to a prime, this simplifies to a prime. And of course, we want this to simplify to a, but this path goes the wrong way, so we have to invert it. We use RA and then invert it. And now we have a sequence of identities which we can compose. Yeah, such a path of a equals to a prime would be given by RIA minus 1, then concatenated with AP to P, concatenated with RA prime. Yeah, and that's if A equals A prime. All right, any questions about this first exercise? That doesn't seem to be the case. Then we'll move on to the next one. Yeah, this one's pretty long, but let's start with the first one and then see if we still need the second one, or maybe you can move on with the third one. But I'm happy to do all of them if that's what you wish. All right, we are given in one our commutative triangle A, H to B, then F to X, and what's it called, G from B to X. And we also assume we have a section of H. Yes, yeah, exercise 2 feels much more like category theory and diagram chasing. Yeah, that's true. You often encounter such simple diagrams in homotopy type theory. But of course, types could be dependent, and you have to worry about higher homotopies because, yeah, we say we have a commuting triangle, but what does it mean for this to commute? This means we have a homotopy H, which witnesses that F is homotopic to G after H. But yeah, this is a type itself, and there could be more than one witness here. Which could be or could not be equal as homotopies. But yeah, you can see it as a generalization of diagram chase. So anyway, we also have the section H and the section S of H, and I'd like to put an H here so I don't forget which function this section belongs to. So we have SH going this way. And we also know that H after SH is homotopic to the identity on B. Okay, and we want to prove that F after SH is homotopic to G. Okay, A F after SH is homotopic to G. Well, F after SH. We know that F is homotopic to G after H. So this translates to G after H after SH. And there's, of course, many things happening here. For one, we are first associating this way. But we already know that a composition is associative, so we might as well drop the parentheses. And it depends on the type theory if it's associative up to a path or judgmentally. But I think here it's judgmentally equal. And well, what is this homotopy? That is really just H whiskered. Yeah, I need a different symbol for this. Whiskered with SH. Okay, yeah, and as I said, we can drop the parentheses, so we could just have G and H here. And if we view it this way, we know that SH is a section here. So this is homotopic to G. One step less, this is homotopic to G after the identity, and that's homotopic to G by the unit laws, and it's immediate to check this. Yeah, that's one direction, and no, that's not one direction. That's the proof of this. And now we assume we have a section of F. Assume we have SF sections of F. And just to remind you again, what is a section of F? That is by definition would be a function SF from X to A, such that F after SF is homotopic to the identity on X. Yeah, and we leave the second component here implicit. So to be very precise, we would have to write SF and the homotopy H SF or something like that. As I wrote here already. Oh, well, no, here it's actually. Well, here I'm assuming the section by itself and not a proof of the section. So it's okay if I'm assuming that SH is the function. Is F after S homotopic to the identity a proposition? No, I'm pretty sure it's not, unless F or S are an equivalence. You could have, well, more than one section of homotopy. Okay, what we're going to prove, a section for G. Okay, so we have this SF going this way now. And we have G going this way, and we need a function from X to B, which cancels G. And well, the naive attempt, since we have so many so much cancellation going on here, is to just take H after SF and check if it computes, and that's what we do. Then we have G. We want to prove that this is a section of G, so H after SF. If this is homotopic to the identity, then H after SF is a section of G. And by reassociating, we get G after H here, but G after H is homotopic to F by a symmetry of homotopies. And by whiskering again, we see that this is homotopic to the identity after SF. Where am I going wrong here? Oh, yeah, not the identity after SF. Sorry, F after SF. That's what I was saying here. G and H, G after H is homotopic to F, so we get F after SF here, and that's of course homotopic to the identity. That's one direction, and the other direction is pretty similar. So we have a section of G, and we want to produce a section of F. Okay, or just write it down clearly once. We have F, H after SF, comma, and this proof, the concatenation of these two proofs here. This is our section of G. Okay, I need more space here. Let me know if this is too small. But now we're assuming, well, maybe I can continue here. Now we're not assuming our section on F anymore, so let's delete this. But we are assuming a section for G. And we want to produce a section for F, and a section for F could be given by going this way, and what goes this way and this way in the diagram, where it's SH after SG. So SH after SG, and we want to prove that this is a section for F, so it needs to be a right inverse. And let's see, what can we do? How do we simplify this? Well, we use commutativity of the diagram again, because then we know that this is homotopic to G after H after SH, F, SH after SG. And of course, this cancels to the identity, then the identity cancels, and then this cancels with that. And all that's left is the identity. Okay, I would, since I think this sheet is pretty long, I would skip exercise 2 of this exercise, well, the second part of this exercise, and move on to the third. And if there are concrete questions, I can come back to it. You can object in the chat if you want. Okay. Now we want to prove that if any of the two is an equivalence in the triangle, then the third one is one as well. So let's draw my triangle again. This is for 3, A, 2, B. G to X, F and H. And well, okay, let's first assume is A, let's assume is equiv H, and yes, is equiv H, and that is by definition equal to sec H and retraction of H. And we also assume is equiv G, sorry, and that is section of G and a retraction of H. Okay, well, a section of G, which we have, gives us a section of F. This implies section of F by part 1. And a retraction of H gives us a retraction of F. Yeah, that's correct. So we get, this gives us a retraction of F. Also by part 2 now. And of course, now we know that F is an equivalence. Okay, in the other case, let's do B assume is equivalent F and is equivalent H. Okay, from is equiv H, we get and prove G, prove is equiv G. From is equiv H, we get a section for G again. Yeah, section for G. No, from is equiv F, we get a section for G. So section for G, we got that. And now the retraction of G, retraction for G, that's a function this way again. And it should contain some retraction in the composition, and we have a retraction of F going this way, RF, and we have H. So let's check if H composed with RF is a retraction for G. So composed with G. This should be homotopic to the identity. Okay, so from part 1, we know that G is homotopic to F after SH. Yeah, that's exactly the statement here. So we can substitute here for the G, and then we have H after the retraction of F after SH. And now this cancels. So this is homotopic to H after SH. And by assumption that SH is a section on H, this is homotopic to the identity. Okay. I think the third is pretty similar. If F and G are an equivalence, then so is H. But if you have questions, by any means, ask them. Otherwise, I'm skipping to the fourth part. Prove that any retraction or section of an equivalence is itself an equivalence. Yeah, okay, so we have an equivalence. Where am I here? We have an equivalence E, call it from A to B. Or actually, let's call it F. No, it's not. Well, it doesn't matter what we call it. We have this equivalence, and we have also a section of it. So an equivalence E, and then a section S. No, B. Okay, so E goes from A to B. This is part 4. B. And these are equivalent via the identity. And we know that E after S is a section. But then the identity is also an equivalence. So by, yes, exactly, by 2 for 3, by the third part, this is an equivalence and this is an equivalence, so this needs to be an equivalence as well. And conversely, if we have E here, some kind of retraction here, A, and B, then we get 2 for 3 here. So R is an equivalence because the other two are in the triangle cubes. All right. Unless there are any questions, I'm moving on. Yeah, consider the type bool generated by true and false. We've seen this before, and observational equality on the booleans in the smallest universe maps equal elements to the unit type and not equal elements to the empty type. And we want to define a map from the identity type of the booleans to the observational equality by path induction. So by, well, it is defined by path induction, and we should define an inverse to this map, or we should prove that it's an equivalence. And here we can actually give a function which is both a left and a right inverse. Okay, I have more space here. So we define, it's called psi in the solutions, from EQ to the prime to B equals B prime. And yeah, by double induction on bool, of course, we can define this by cases. So we first define psi true, true, true. And this is a map which goes from 1 to, well, from the unit type to true equals true. And well, we only have one element to assign here by a unit induction, and well, what's in true equals true. Let's take reflexivity at true. And let's also do the next one, psi true false. This is a map from the empty type to true equals false. And well, we get this map by yeah, by the induction principle of the empty type. We just get a unique map going this way. So empty induction. And the other cases are similar. So if we replace true, true by false, false, we are in the same type on the left, but we have false in the identity type. And of course, we need to map to reflexivity at false. If we swap true and false here, then true and false are swapped here as well. But we can still use empty induction. Okay. Yeah, and I think it's also immediate that that's an inverse. If we compose, if we go from one way, from this way to that, we map to the only element that's there, which is the style, which maps back to reflexivity, and that's what it's defined on. For the empty type, it always commutes, so this will always commute, and similar in the other case. So I would say that's done. Now here is also a remark. It's easy to show that 1 is not equal to 0. And maybe let's repeat this proof because it's not done in the solutions. So we have transport, and transport can take transport as an element of a pi type, and it has two parameters, A and B, and these are terms in any type. And since universes are types, we can assume this for types in the universe. And this turns an identity into a map for type families over the universe. So we have C, well, in a view, let's assume we have a type family C, A in type. This gives us a map from CA to CB. And now if we take C to be the identity and plug in for A and B just 1 and 0, then get transport on the unit type and the empty type. That's from 1 equals 0 to 1 to 0. Yeah. And this implies, of course, that if we have such an element, we can construct an empty one. Okay. Yeah, as a consequence, we can prove this. But we've seen that before also in Magda. Okay, now we're supposed to prove that the constant map in the Booleans, so the type isn't given here, but we of course mean const, let's do it here, const B goes from bool to bool. I'm spelling this out. Bool to bool. And that's just always B, so true gets mapped to B and false gets mapped to B. And that shouldn't be an equivalence, and I really hope that it's not. But for the sake of contradiction, assume const B is with then const B has a retraction. And having a retraction by exercise 1 means it's injective. And const B is injective. And what does that mean? That means that const B of true, which is by the definition equal to B, which is also by definition equal to const B at false. Yeah, that this implies true equals false. But we know that true is not equal to false, and so this implies the empty type, and that's a contradiction. And well, the second proof that bool is not equivalent to the unit type is really just the same. If we have a type with 2 elements, it shouldn't be equivalent to a type with 1 element. Here we also assume an equivalence, which maps to star, well, which is constant at star, constantly star, and that's injective. And by the same equation here, we would get true equals false, and a contradiction. Exercise 5, unless there are objections. Okay, let A be a type and B be a type family over A. For each x and y in A, construct an inverse of the function which inverts the paths from x to y. You can also do it directly from the section instead of invoking problem 1. You mean we have 1. This is an equivalence, and this has a section S. So E after S is the topic to the identity on 1. Are you sure you mean the section? Which one? Yeah. Part 1 of question 4. Yeah. Yes. I mean, I guess, yeah. If from the section you get a subjective map, and const isn't subjective. Yeah, it's neither surjective nor injective, and you can reach a contradiction both ways. Yeah, that's true. Okay. We are constructing an inverse to the path inversion. And well, unsurprisingly, we're mapping out of the path here. We have a dependent family over this path, and we use path induction. So we construct an inverse of the function, where we construct in x, y to inverse from y equals x to x equals y, and by path induction, it suffices to give inverse x inverse from x equals x to x equals x. And of course, we can map reflex to reflex. And similarly for the yeah, it is indeed. What this defines here is really so inverse path induction. I mean, well, if we define the inverse of inverse like that, we do get that inverse xy is at least homotopic to inverse yx. And the question is there a smart way of defining inverse here? Is there a smart way of defining inverse inverse such that this is a judgmental equality? And I would say I think since we in both ways we only need to define on REFL, it doesn't matter by the path induction. But I would yeah, I don't know right now. I have to sit down and do this on my own, and then I'll let you know on the Discord which conclusion I came to. But either way, the inverse, that their inverse is trivial up to a path. But I'm going to have to write down the induction terms to see if it's judgmental. Well, yeah. Okay, yeah, sorry about that. Let's move on to the transport operation, and I get back to this on Discord. Yeah, transport b of p from b of x to b of y. Oh, it's not completely obvious why it's actually an inverse. Okay, well, yeah, let's assume we define it this way. And we want to prove that inverse xy inverse after inverse xy without an inverse here at the path p is homotopic to p, and this for all p in x equals y. And now we use path induction again on this path. And then we only need to check that inverse x, y, inverse, sorry, x is now judgmentally equal to y, inverse x, x, roughly x, that this wait, on the topic. Sorry, equal here. Equal to p, equal to roughly x. And that's true by definition. This is roughly x, and this is roughly x by definition. Is it clear now? Or should I do the other direction as well? Okay. Okay. Yeah. Inverse. This is also defined by path induction. And it's also defined by path induction sending refl x to refl x. We don't just assume any function from x equals y to y equals x. We assume the one defined by path induction. Yeah. But good question. That's certainly a requirement. Okay, now an inverse to transport. We want to define transport B P inverse from B of y to B of x. And well, we also have, let's write it like this, P x equals y. And we also define this by path induction. And in this case, there is also a second way of defining it, but we get to that. So first, let's define this by path induction. Well, by path induction, oh, this should be x equals y. By path induction, we only need a map from bx to bx, transport b inverse refl x, and we take this to be the identity of bx. And that's an inverse. But we can see, we should be able to see, let's see if we actually see it, that transport B of P or transport inverse of P is the same as, okay, I'm running out of space here. So transport in B at P, but the inverse transport, this is homotopic to transport in B, the regular transport, but with P inverted, inverse P. Inverse of P, so like this. As types, as functions from by to bx. And how do we check this again? Well, this is a statement which states that some equality holds for all p, and there's nothing preventing us from applying path induction. And then we need to check that refl is refl in x again. Yeah. So this is an important identity to keep in mind. By function extensionality, of course, this homotopy turns into a path. If we invert the transport operation, it's the same as transporting along the inverted path. Okay. Let's check what time it is. 14 more minutes, so we should move on. What's the point of these exercises? We are just proving that homotopies satisfy the properties you'd expect from homotopies, and the proofs are tedious but straightforward. Yes. Well, one reason is that we still need to prove that the homotopies actually behave the way homotopies do. Because if you come from homotopy theory and then look at the type for all x in A, fx equals gx, it's not immediately clear that this behaves like homotopies. Plus, I'd say an additional argument is that in the lecture there just isn't enough time to prove all of these exercises. but I agree. I mean, if you know a lot of homotopy theory and category theory, and maybe have seen some type theory or whatever, maybe seen the semantics, then it's not surprising, and you can skip those. But I'm sure for many people it's quite useful to do these. But if you think that the exercises are too easy, there is also no triple star exercise on this sheet. We can make sure that there are more difficult exercises in the future. We've had some discussion about this among the teaching assistants, but we came to the conclusion that the students who want more difficult exercises already find them by themselves in the book, and then talk about those on Discord. Does it answer your question? Okay. Okay, we have F and G from A to B, and I think this level is perfect for me. Yeah, that's great. Good to hear. Okay, we have two homotopic functions, and we want to prove that if one is an equivalence, then the second is one as well. So of course it suffices to go only one way by symmetry, and let's go this way. We assume that F is an equivalence, and that means we have I use the same notation as in the solution because otherwise I mess this up now. That means we have H, TH. So H will be a section of F, and TH will be a witness that H is a section of F. We have K, which is a retraction of F, and TK, which witnesses that K is a retraction of F. So sec F, and retraction F. We assume this. So, and yeah, okay. We want to show that H is retraction H where H is a section of B, section of G, and K is section of G as well. Sorry, retraction. So what this tells us, if we have homotopic functions and one is an equivalence, then also the inverses of one function are inverses of the second function, and this is what we need to prove. So we need to show that G after H is homotopic to the identity, but G after H is by assumption on by this homotopy. G is homotopic to F, so we can invert it and then whisker. So that gives us F after H, and that's just the identity by the assumption that H is a section for F. And similarly, we want to show that K after G is homotopic to the identity, but K after G is homotopic to K after F, and K after F is homotopic to the identity by assumption that K is a retraction. And yeah, so to be formally correct, we need to concatenate here these homotopies and give those proofs some name, and then we get a tuple like this with the same H, the same K, but different proofs here, which gives a retraction of G, a section of G, and a retraction of G. Yeah, okay, and going the other way, you can of course prove the same thing by the same argument, or you can show that this gives us a homotopy H-1 from G to F, and then apply what we just proved. Final exercise. Suppose that E and E prime are equivalences between the same types, and E is homotopic to E prime. Let S and S prime denote the sections of E and E prime respectively. Prove that S and S prime are homotopic. Okay, so first, if we have such an equivalence, we can show that such a section is also a retraction. So we have the section S of E. We know E after S is homotopic to the identity, and E prime after S prime is homotopic to the identity. We want to show S is homotopic to S prime, and we first have a lemma, and that's that S homotopic to E. S after E is homotopic to the identity, so S is also a retraction. Well, what is S after E? That's just R after E after S after E. So E has some retraction, and let's call this retraction of ER. So this is the identity, and we might compose with the identity on the left. Then we reassociate, and by assumption that S is a section for E, this becomes R after E. And then again, by assumption that R is a retraction for E, this is just the identity. So any section of an equivalence is also a retraction of that equivalence. And this we can use to show that S is homotopic to S prime after E prime after S. So here we've added one again, S prime, but this lemma S prime is a retraction of E prime. Then we want to use that E prime is homotopic to E. So S prime, this is homotopic to S prime composed with E, composed with S. And of course, by assumption that S is a section for E, that's just S prime after identity, and that's just S prime. Yeah, okay, so we've proven that for any homotopy equivalences, sections of one equivalence are also homotopy to sections of the other. The same goes also for retractions, also by symmetry again. Yeah, and that's all I have to say. Are there any further questions? That doesn't seem to be the case, unless you're still typing now. I can't see if anyone is typing. Thank you for attending my exercise session. You posed some very good questions, and it was also fun for me, and I got back to you about the judgmental equality on the 5th exercise on Discord. Thanks. I'll stop the recording now, but I'll stay in the room until the hour is full.